Okay, there's a supporting rods. There's a horizontal beam. And there's a swing. No? So the swing, what will happen will be like this. Okay, this is so now the swing will be, it is going to swing like this, no? Okay, Jula, somebody, some Jula, I think Telugu, what you call. This will be like a Jula, no? So this will be. Okay, now you do one thing. Let be a small kid. That one. You just give some slight push and you go and sit here. Be away. What will happen to this thing? It will oscillate and will come to rest. No? Again, the kid will cry. Then again, you give some push. It will oscillate. The moment it stops, the kid will cry. This is what happens. Why do it will come to rest? Why did it come to rest? When the swing, when the particular, like there's supporting, you can say like a plank or something, this plank, okay, there's a plank we'll call. These are the strings. Okay, no. Why the, if you give some push and release, the swing, what will happen? Will oscillate and finally will come to rest. Okay, tell me like why it happens? Anybody?
Sir, reaction force with the beam.
Reaction force with the?
It beams. Hinges.
Okay, there'll be a, you say there'll be a friction here. Okay, I'll apply grease. All of you know grease, Grease, grease for vehicles. I'll put some oil, grease. Okay, I'll minimize it. Okay, tell me. Now also it will come to rest. Yeah.
Sir, air drag.
Hey, drag. That's all. There'll be a whisker drag will be there. No, there'll be a whisker drag. So in fact, it is oscillating. This will be the path of the motion of the swing. I'll show the physical diagram. So initially I'll give velocity V naught. So as it is swinging, the kid come plank, everything. So when it is have no, so here the viscous drag will be there. Okay, fine. So this is, so again, when the swing comes, both the viscous drag will always act opposite to velocity, no? So when it is having velocity, say V1, viscous drag, V2, the viscous drag. So again here, FV naught. Here it will have less velocity, FV3. Again, the swing goes here, V4. Tell me like how the viscous drag will be always act opposite to the velocity of the that particular plank and kid that swing. So because of the viscous drag, it will oscillate and finally come to rest. So how the path of the swing will be? The swing initially it will be like this. I'm showing the amplitude. Okay, fine. Why do this one? This is the A drag. There'll be an A drag will be there. Okay, now what you do is like to maintain that amplitude fixed here. So there's an initial, it should have been amplitude. Huh? But what will happen to amplitude keeps on decreases, come to rest. To maintain the same amplitude, what you should do, how much of energy decreases per cycle? What is a per cycle? The one cycle is this one. Huh? There's a one cycle. What is a one cycle? It goes, there's a mean position. I'll come to the mathematics first. Let me understand. Let me explain through diagram so that'll be easy for you. What is the mass involved here? So what is the one oscillation? The one oscillation is like this. Huh? For every oscillation, viscous drag will consume some energy, no? So therefore, the amplitude of oscillation keeps on decreases. Once it comes to it, the kid will cry. Again, what happened? The parent who is there, who is caretaker of that kid or parent or somebody is there, no? Again, what you'll do, you'll come and you'll give some push. Again, it will start oscillating. The kid will feel happy. I think this is what happens in garden. So next time when you go to the park, everything, do play. If it is meant for, if it is meant for kid, okay, play it. Since I think you're grown up now, you are an adult. I don't think so. You have a chance now. So if it is really meant for you, yes, you can play it. Okay, this one. So now, what is the remedy for this? So I want it, the oscillations will happen. The kid should not cry. So what I should do? How much of energy it decreases in one oscillation, that much if I continuously supply, what will happen to that amplitude? Will remain fixed. Agreed? So because here, say like when the block moves from here to here, the viscous drag does negative work. So oscillation energy decreases. So like that, what I should do? How much of energy decreases in one oscillation? That much of energy, if I continuously supply, what will happen to this swing? It will maintain a constant amplitude and the kid will never cry. This is what happens here. So if you just give one push and go away and sit, the, the swing will swing and will finally come to rest. Okay, what I should do? For the amplitude to remain same, I must give energy equal to energy dissipated. So continuously. So usually what happens, did you notice? The person will give just one push, will go and sit, or continuously will be giving push. Continuously I'll be giving push, no? Am I right? Or some kid who are a little bit grown up, no? If their legs can touch the ground, what they do? They'll be kicking the ground, no? To impart energy. So will they kick only once or they'll kick continuously? They'll kick continuously, they'll kick the ground, or somebody will be continuously pushing the swing. So at what rate I'll be supplying energy? Because here the energy is decreasing. I should supply energy. So I'm going to supply energy continuously, no, at a rate, because say I'll push. Again, when the swing comes, again I'll push. Like that continuously I'll be pushing it. So while I'm pushing also, there is some sort of, like you can say like in 1 second, how many times I pushed, that will become frequency. So shall I say driving force has come into picture. What is the driving force? Because the swing, for it to what happen, to oscillate continuously, to happen, we should supply energy continuously. I should apply a driving force. I should apply a force. And what is the frequency of force? Or is it like that I will run along with the swing? Is it advisable? Or I should stand here, I'll push it. Again, when the swing comes, again I'll push it. Am I right, all of you? So it is here, no, I'll push it. Again, when the swing comes, again I'll push it. Like that, what happen? When the swing is oscillating, what happen? I'll be pushing it. I'll be pushing it at a certain frequency, no? Because continuously for certain interval of time, I'll push it, I'll wait. Then again, when the swing comes, again I'll push it. So like this, I'll be applying a force. And how do that force? That force will vary with the time. That's called like a driving force or driving frequency. And the swing is oscillating frequency. Okay, what should happen here now? The rate at which energy decreases, at that rate you supply energy, yes, it will oscillate with constant amplitude. Now, if you push more such that what happen, the energy supplied is greater than the dissipated. What will happen? If you push more and more, the swing, what happen, may go and it may go up to till here, no, the kid may fall, no. There's also very problematic. Okay, don't keep kid and experiment. You sit and experiment. You may fall, you can adjust, but the kid cannot adjust. So therefore, you do one thing in this plank, you keep any sort of block or something which will not slip. That one. Then give small displace, small push here. It will oscillate. Continuously push it. Now, as you keep on, if you rigorously start pushing this one, at one instant open, as the swing will go up till here, and what all you kept object may fall. So I think there are two cases are there, no? So three cases are there. One, okay, how much energy needed? If you supply that, it will maintain its oscillation. If you supply energy less than which is required, as it will be like this. If you supply energy required more than this, what happen? It will swing rigorously and the kid may fall. Two things are there. So of all, what is very important? So it should swing with a constant angular amplitude. Say let this be say 30 degrees. It should not swing more than 30 degrees. So then, so how much of energy lost, that much of energy you supply, is it will have the same amplitude. They're called like a resonance. Means at what frequency this particular swing is swinging. At that frequency you supply energy, then resonance occurs. Then what will happen? Then what happen? The kid will feel comfortable. If you supply at a energy at a frequency less than the frequency required, the frequency of oscillation of the swing, then what happen? It will be off like this. If you supply at a frequency more than the oscillating frequency, then what happen? Will not be at resonance. Again, the kid may fall. The best example with the swing, you can try, don't take kid and experiment. I'm telling this one. You can take your friend and you can do that experiment. So like that, we have many examples here. This is one practically what we see in the garden, in the park, is what I took example. So therefore now what is the thing? The driving frequency will come into picture. When forced oscillation is there, no, the driving frequency will come. So now how to express here? Now I'm going to apply a driving force. The force which will vary harmonically with the time. So why that one? Because I think you'll be continuously pushing this particular plank, no? You'll be continuously pushing this plank means continuously you're applying a force. And how do that force? That force will vary harmonically. So that's what we call, it's a driving force. So I'll write it F of FD, I'll write it. There's a driving force. So this should be equal to F naught cos omega dt. What is omega d? Driving angular frequency. What is omega naught, or driving angular frequency? Or in terms of swing, can you say, sir, what do you mean by driving angular frequency? The rate at which person pushes the swing. This is in common, this is a technical language. In terms of common language, what's happened? Just like the rate at which person pushes the swing means per second how many times you push. Simplest idea. You'll be pushing with a certain force F naught. This what here. Okay, now what is the resultant equation of SHM will be M. So what are the forces that will be acting? M of AT equal to minus there'll be viscous drag also will be present, and this driving frequency. All together, they are acting on this particular system. Okay, this will be m d square x by dt square minus this will be k x of t. This will be bv or b dx by dt. There's a viscous drag like or damping force, and there's a driving force. What is the driving force? F naught cos omega t dt. This again equation of SHM only. So what is this driving force, or you can call like what is FD? FD is what? Driving force or external periodic force. So when you apply this driving force, what will happen? The swing what will happen now will start vibrating with this particular driving force frequency. So therefore now, so what is the basic? We'll write it here. I'll write some explanation. When we apply the external periodic force FD, the oscillations natural frequency die out. I'll write it here. Die out, and then the body finally oscillates with the angular frequency of the external periodic force. Okay, no, so the displacement is given by A naught cos omega d, this one, not omega naught. Then what about the amplitude? The amplitude, so okay, okay, this is, sorry, this is a, no, this will be, this amplitude is given by F naught. Remember formula, sir, don't bother, sir, how you wrote all this one. At your level, not possible to show mathematically. Tan phi is given by minus of V naught Okay, no, so this is what is so what is V naught X naught? So you can ask, sir, what is V naught? Initial velocity and X naught. So means here what you give initial some velocity to this swing, that is V naught. Initially it's at some position, no? You may give somewhere from here. So that is what X naught here. So V naught and X naught. Initial velocity and initial displacement at t equal to 0. Okay, now there are two ways are there. First, omega d equal to omega, then omega d very much greater than omega. We'll break up the discussion in two parts. Omega d greater than omega and omega d for that one. So first cases we'll discuss here. Small damping, small damping, driving frequency far from natural frequency. Far from natural frequency means like greater than, you can put it here. So here what we write it, omega dB will be much smaller than m omega square omega d square. This is a condition. Then what is the amplitude of oscillation? It is given by F naught Okay, agree this. So this is the condition I put when driving frequency far from natural. Far means very much in terms of this one here. Now, what is the meaning of this small damping? Driving frequency far from natural frequency. So what is the meaning of this? So when this condition arises here, so they say small damping, there'll be some damping, or don't say there's no damping. There'll be some damping this one. So when this condition arises, put like this. So sir, can you say in terms of swing? So when this happens, so when your timing of time period of oscillation of swing, if it is equal to time period of oscillation of push, what will happen to this one? When omega equal to omega d, what do you mean by this? The amplitude will become infinity. But practically what happens? there'll be some damping will be there. So therefore it cannot be infinity. You can say very large. So when you get that large amplitude, when omega equal to omega d, this is what I wanted to say. When the time period at which you are pushing, if it is equal to time period of oscillation of the swing, then what will happen? The amplitude will be infinity. Practically, it will be very large. So we are not understanding. You see, like if you set free the swing, it will take some time to oscillate. No, there's a time period. At the same time period, if you apply driving force, means you'll be pushing it at the same time period. Then what will happen? The amplitude will become infinity or will become very large. But practically what will happen? Here, not infinity will become very large because there'll be some damping will be there. Even this what happens in small damping. So therefore, what we should do to have this small damping, we should apply grease where at the suspension here. We should apply grease here between bearings and that particular string. No, if I apply a grease, what will happen? Small damping will result because of small damping. And if you start pushing with a frequency equal to natural frequency of the swing, then what happen? We'll get a very good amplitude, not infinity, large. This is what we have to take care here. So ideally, if omega equal to omega d, A will be infinity. Practically, A will be very large. There's a meaning of that one. This condition is, if it is applicable like this, then we can go for here. So when you write, when omega d is equal to omega, A tends to infinity. Practically, it will be large, not infinity. It cannot be what happened. Practically it will be large due to some damp, because small damping you're saying, you're not saying damping zero, small damping will be there because of small damping. Okay, there's a one mathematical condition you can put it. So second one, driving frequency close to natural frequency. Omega d will be very close to omega in this case. So what will happen? The equation will become A is equal to F naught by omega dB. It will be very confusion. When omega equal to omega d, I think if you want, I'll take it out this, because you're telling the sir, why don't you substitute this and bring this one after this condition for amplitude to be large. Again, if you make equal, there's a separate case here. If you want, I'll remove it here. Some students are getting confused. Sir, again, you wrote this one for explanation purpose. When amplitude will be infinity, again, when the driving frequency equal to natural frequency of the swing. So that will be very confusion for you mathematically. So let me put here. Now there's a thing, when driving frequency close to the natural frequency here, then the amplitude is given by this particular formula. This is called like a resonance here. It can never be infinity until this one. Omega equal to omega, it can never be infinity. It'll be very large here, this one. So this particular condition is called like a resonance. When equal to natural frequency, when driving frequency equal to natural frequency, then energy lost per cycle is supplied by an X agent maintaining amplitude constant. So this is called as, this phenomena is called as resonance. Means how much of energy lost per cycle, that much of energy if I supply, the amplitude remains constant. I that is called like a resonance. I think when the kid will enjoy the swing, how much of energy is decreasing per cycle, that much of energy if you continuously supply, then the swing will have a constant amplitude. The kid will feel present. So therefore, when you go for the swing, when kid is sitting, no, as you start pushing the swing, what you have to do? It's a skill. You cannot just push in your own way. How much what will happen? How much of energy decreasing per cycle? That much of energy if you supply, no. So nothing but what happen? A resonance is occurred. So what is the resonance? The the frequency at which you are supplying energy is equal to the natural frequency of the swing. Because of that, resonance will occur and the amplitude remains constant. I think this is what needed for swing, no. So this called, so it is very important in some machines all. So for at our level in mechanics, no, I can give this swing as an example. Maintaining amplitude, so, so by an X-ray agent, maintaining amplitude constant, I'm telling. Here what will happen, amplitude constant in the sense the amplitude increases. It will become some fixed, very, you can say, appreciable value. So that particular phenomena is called as a resonance here. Or I think by an X-ray agent maintaining increase in amplitude, I'll write it. This will be better technically. This phenomena is called as resonance. Okay, no, so these are the some types of questions, the only technical. So just only, I think you have to remember formula. At resonance, the amplitude of the force losses is given by this one. Small damping, driving frequency far away, this is the equation what we have. This called like a forced oscillation. What do you mean by forced oscillation? So now you may ask like, sir, can you give other than spring any example? Okay, let me take a spring. So the here is what I'll apply driving force myself. This one. So along with this, here spring force will be acting. Mg if it is having velocity, here viscous drag. Even if you want buoyancy in due to air, that also you can bring. This particular thing, I will making it to vibrate. So when this will have large amplitude, when this driving force becomes equal to natural frequency of the block, this end of the spring is not, it's like it's not a fixed here. This I'll be moving up and down. Okay, this point will be moving up and down. We will move, and like a person holding this, what happened will be moving it up and down. Okay, I think I'll show the hand. Some of you are finding difficult. Okay, this is spring, no? How to show finger? Okay, I'll bring it. I'm unable to show. I'll try it later on. So here it will be like this. Huh? Person holding this end and moves up and down. That one. This is driving frequency. So what happened? The block will oscillate. Here what happened? We have a damping effect, everything. So when this driving frequency becomes equal to natural frequency of the block, then this will have a very large amplitude. This is called like a resonance. This is what very important is. So when this block will have maximum amplitude when the driving frequency becomes equal to the natural frequency of the block. So here the block will have, the block will oscillate with maximum amplitude when omega d, when driving frequency becomes equal to natural frequency of oscillation of block, called as resonance. Okay, this is simplest thing. So when this will have maximum amplitude, when this will also have maximum amplitude, when the driving frequency means I'll be moving up and down. This particular, what is this force? This force which I'll be apply will be of this kind of. F naught is a force cos omega t. Okay, I agree this. So this is the basic idea. This is called like a forced oscillation. You are forcing it to oscillate. You are not permitting it to oscillate on its own. You are forcing it to oscillate according to your convenience. That's all called like a forced oscillation. So here at this particular end, I'll be pulling it up and down. This will oscillate. Okay, here we can show like this. Agree? No? This is the order, this arrow. It shows the vibrations of this one. Okay, this is about again